All right. How you guys doing? So, I did not yet update the syllabus, but I want to take a look with you real quick where we're at. I owe you a homework. It'll be a relatively short one, so I will get that posted for you today as soon as I can, and that'll be due on Tuesday next week because that's going to be our exam review day. So we are going to basically cover the rest of coagulation and flocculation today. You have the weekend and until Tuesday to do that homework. We'll go over the homework together on Tuesday, and then your first exam will be on Thursday next week. So semester's really sneaking up on me here, but I'll update the syllabus here and post that to Moodle, and I'll get you that homework posted for you very soon. Okay, but I don't think it'll be too crazy or too terribly involved because kind of the first section is two smaller homeworks, sort of. So I think it'll be all right, and as you know, it's completion anyway. So, all right, so that's a little quick touch on where we're at here. Today, like I said, we'll wrap up the coagulation where we left off and talk about flocculation. Any questions before I dive in? All right, and if it wasn't obvious, what we've covered so far up to and including flocculation is the content for exam 1. We're not going to do anything on filtration for that. All the filtration, disinfection stuff will be exam 2. All right, so coagulation, flocculation. We left off here talking about this effect that particles and surfaces have in water where the charge of some surface can extend out and reach and kind of push other particles away, typically because they're both negatively charged. So it's kind of the stiff arm approach. We did a little diagram and showed that kind of the particles repelling each other up until the point where they get close enough, and then once they're close, then there's attractive forces that will outcompete the repulsion forces, and they'll stick together, and the ions tend to get out of the way a little bit, and they're stuck together. So the question then is, well, how effective is it? How much? What can we do about it? And what does this look like if we look at some data? I mentioned last time that if we take charges that are more than just one charge, so if each one of these is, let's say, a sodium, so one little atom for one charge, and maybe chloride for the negative, those are relatively small, but they each just have one charge. If we take something like calcium that has a 2+ charge, it's not much bigger than the sodium, but it's taking up twice as much charge. And so it would shrink that layer and compress it. Likewise, an aluminum is also not a very much larger atom, but it has 3 times the charge of sodium. So it's going to really shrink the amount of charge that's dispersing into the solution. So by adding in highly charged species, and the same is true for negative stuff, highly charged stuff will compress that double layer action. So this slide, what I'm looking at here is showing just that. And I'm going to start on the larger figure here. What we're looking at here is the relative turbidity. So turbidity is a fancy word to say how many particles are scattering light in solution. So it's like, if you look at my water bottle, you can kind of see through it pretty well. But if I were to shake it to the point where I've got lots and lots of small bubbles, at least while those bubbles are there, the water is pretty turbid. So if you've ever seen like the drinking water fountain give this weird milky looking color of water, occasionally it happens. It's actually really tiny fine bubbles. If you let it sit there for a little while, the bubbles will come out. But while they're there, it kind of looks like milk because it's so much turbidity. So turbidity is just particles that are scattering light. So it's a measurement of the particles that we're trying to remove. So if you look in a lake and you can't see past a few inches, it's very turbid. Whereas if you look in a big thing of, I don't know, Kool-Aid, it might be colored, but it's clear in terms of particles aren't scattering the light if it's all dissolved, right? So there's a difference between light absorption, some of it's being taken up, and scattering where it gets cloudy. Okay, so we're looking at the cloudy stuff because that's showing us how many particles are there. So when we see relative turbidity, that means at 100%, it's fully cloudy. However many particles are there, they're still there. So when we see the turbidity drop, that means we've caused the particles to stick together, and then we can remove them. So this graph is just showing it's fully dirty up here, and then at some point it drops, and we have the impact that we want it to. So that's just saying at what point does adding some salt here, some aluminum or calcium or sodium, have the desired impact of shrinking that double layer and causing the particles to stick together and be removed. So this is a measurement of when essentially the adding salt works. So how much salt do we need is kind of the question that this graph answers. And what we're looking at is how much salt for each of these different types. And so sodium, maybe sodium chloride, that's our typical table salt, right? That, if we add enough sodium, we need 10,000 milligrams per liter. That's 10 grams per liter. That's like a third or maybe a little more or so the saltiness of seawater. So we're getting to the point where we're almost drinking seawater in order to clean it if we're using sodium. So clearly not a great approach. So this is 10 grams per liter. Seawater is about 25 to 30 range grams per liter of salt. Lake Pontchartrain in some parts is maybe 5 grams per liter, just as a reference. So sodium, not a great idea to add that in order to cause particles to stick together. But if we look at calcium, just with a 2+, now we're looking at 100 milligrams per liter. It's quite a bit lower, 100 times smaller concentration. And that's at a point where, okay, maybe that could be relevant. Well, if we go down to aluminum, now we're at 10 milligrams per liter. And the nice thing about both about calcium and aluminum is we can precipitate those a bit easier. Sodium doesn't really react with too much that form some precipitate, but aluminum, it's very easy to precipitate. We just manipulate the pH a little, and then we get aluminum hydroxides, and we can then remove it very easily. So when we do coagulation, if we're going to select the saltiness approach, causing that compression of the double layer by adding more charged ions. So another thing to think about is, in this condition, those ions will reach further into solution if there are fewer ions, because the surface didn't change charge, but the solution doesn't have as many charges, so they're pulled out by osmotic pressure and they are lengthened. So if we have very, very clean water, it's going to be a very, very long double layer. Whereas if we have very, very salty or highly ionic water, it's going to compress it. That's actually, I mentioned this before, but with a water hardness, this is the action that makes soap feel different, right? If you have very, very soft water, this tends to be a further thing, and it feels like you can't quite get the stuff off the surface of your soap. Whereas the hard water will compress this and make the soap bubbles even less likely to form for this type of effect. Okay, so that's one way to look at it. Another couple graphs here on the left. This is actually the distance measured into solution in nanometers, a very small distance. How far can you feel the charge? That's what these are showing. And so if you try with 60 versus 600 versus 6,000 milligrams per liter of sodium chloride, well, you can have some distance out into solution. And if we look closely, maybe this y-axis is some charge, like the surface potential in millivolts. So if we just arbitrarily take 20 millivolts and say, how far into solution does that go? Well, we get about 20 nanometers with a dilute, And we could push it all the way down to a few nanometers with 6,000 milligrams per liter. And we saw that it takes about 6 to 10,000 milligrams per liter before we see that effect. So something like that is the relevant amount of charge and the relevant distance. We could also look at, instead of sodium chloride, what if we use, let's say, Z equals 1, that's the charge, that would be sodium. Well, what if we used calcium, right? What would that look like given some set amount, and I think this is 10 milligrams per liter, and we see the same function, right? If we use aluminum instead of sodium, it shrinks it. That's all we're saying here is it's traveling less far into solution before we can no longer sense that charge. So all that to say, we can shrink that electrical double layer by making it saltier, especially if we use the highly charged stuff. That's kind of the concept here. So that's what we end up doing. We destabilize particles, cause them to stick together, and we do so by really increasing what's called the ionic strength. Now, this is one last little chemistry term. It's quite simple. When we calculate the ionic strength, we're calculating the total charge in solution in a way. So the ionic strength I, and you'll have this formula on the exam, is equal to 1/2 times the sum of each concentration of a charged species times its charge squared. Now we are counting the number of charges, not the mass, right? So we're going to have to use molar units. So what that looks like in practice, I'll work this one with you here, is if we calculate the ionic strength for magnesium chloride, MgCl2, magnesium chloride will dissolve to give us magnesium, 2+, and 2 chlorides. So each chloride having a -1 charge. So when we calculate the ionic strength, what that will look like is 1/2 times the concentration of magnesium times its charge, which is 2+, squared, plus the concentration of chloride, Cl-, times its charge, which is -1. Squaring it gets rid of the negative, which is quite nice. And that will give us our answer. So all we really need to do is to be able to calculate the concentration of the magnesium and the chloride. So here is where we need to do just a tiny bit of math, tiny bit of chemistry to see, all right, if we dissolve, for example, 100 milligrams per liter of magnesium chloride, then we need to find those concentrations, right? So now we need to look up the molecular weights or atomic weights for magnesium and chloride. And I don't have that. Let's see. I think magnesium is somewhere around 24 and chloride should be 35.45. All right. Someone try to find the atomic weight for magnesium before I can. Too slow, 24.3. All right. I thought you guys were all on your phones. What happened? You paying attention to my lecture or something? All right. Jokes aside, we've got those. So now take a moment. I'll start working through this with you in just a second, but take a moment just to think about, okay, how do I solve the problem? Just to get your gears spinning here. All right, so we should have the molecular weight if we add in, I did that wrong, sorry. Just ignore me for a moment. I did 2 magnesiums and 1 chloride for some reason. 35. Okay. The molecular weight, if we do it properly, ought to be 95.2 grams per mole. 2 chlorides and 1 magnesium. And we were given 100 milligrams per liter, so hopefully you were starting to think, okay, I need to convert that from mass to moles, which is why we're doing the molecular weight in the first place. So we can say this is like, we could do the conversion probably in our head to say, well, that's 0.1 grams per liter. And then divide that by the 95.2 grams per mole. That's going to let the grams cancel and the moles will come on top. And so if we bring this over here. Oops. So if we take 0.1 divided by 95.2, 0.00105. And that should be moles per liter. And that's the number of moles of magnesium chloride we dissolved in 1 liter of water, essentially. So from there, we need to say, okay, well, how many moles of chloride are formed and how many moles of magnesium are formed? Because what we just found was we have a 1 here and a 1 here and a 2 here. So what we just solved was for the amount of this stuff. So now we need to say, okay, well, if we got 1 mole of that, it's 1 mole of magnesium. So therefore, if we had 0.00105 moles, that's going to be that same number of magnesium. So that's going to be the answer to our magnesium, 2 plus. But our chloride, we have to multiply by 2. So we can go ahead and write this in 0.00105 moles per liter, capital M. And if we double that, that should be 0.00210 moles per liter there. Okay, so that's like the part that we have to make sure that we get right in the sense of doing the conversion to moles per liter. And recognize also that if we had other sources of chloride, we would have to add that into the total chloride concentration here, because what we're showing in each one of these is the total amount of magnesium in solution. Doesn't matter where it comes from, there's that much amount. Right? So anytime we're working with this, you could have magnesium chloride and sodium chloride, for example. Maybe I have an example problem for that. Okay, so then if we put these numbers into place, let's see if I can do it, times, we'll say that 0.00105 times 4. So I'm multiplying by 4, that's the 2 squared. So I'm just filling in my equation right now. So I've done magnesium, so 1/2 times magnesium times 4, and now I'm going to add the chloride. That'll be times -1 squared, which is just 1. So I'm just going to leave that off. Okay, and our answer should be 0.0063. This is kind of like a moles per liter unit. It's not exactly that. 0.006. So you can call it moles per liter. It's kind of moles charge per liter, sort of, but don't worry too much about it. If this is one case where don't worry too much about the units there. Okay, so that's just one way we can express the amount of charge in solution. It's nothing new in terms of using like any new chemistry. It's just a formula. We have to do a tiny bit of chemistry to use it, right? So those would be our answers here. We've got another potential example. For the sake of going a little quicker today, I'm going to just give this for you to do on your own if you'd like to, but I'll start it real quick to show you. This is a good example of that magnesium chloride with the sodium chloride. So what we would do is we would say, well, we have some amount of magnesium from magnesium chloride and chloride, and then we have some amount of sodium, and then we also have chloride coming from the other one. So the chloride, when we calculate it, would be equal to the amount added from the magnesium chloride plus the amount added from the other one, right? It sounds obvious when I say it, but we're only going to include it in our ionic strength calculation once, because when we say the concentration of chloride, we're meaning the total concentration, right? That's the concentration of the solution. So this is going to be the Cl from MgCl2 and the Cl from sodium chloride. I'm just going to write it this way as a shorthand just to say that's where it's coming from. And then we're also going to have some sodium and some magnesium. So we need to find each one of those. And then, of course, our ionic strength equation would look like this. Okay, does that make sense? And again, this is assuming that both magnesium chloride and sodium chloride dissolve completely, and that's typical at this range, right? You'd have to add quite a lot before they're not going to dissolve. Okay, makes sense how you would approach that? Might be good practice if you're feeling uncomfortable with it. Just make sure you're taking the approach that both of these species are going to add the stuff, and you're just finding the total amount that was added. All right. So once we have added our coagulation, and essentially what we've done is destabilize the particles, so now they're ready to stick together. At this point, our aim is now to intentionally let them stick together. So the coagulation step from a design perspective is quite simple. We just mix it real fast. We add whatever coagulant we're going to add and mix it real fast. Then everything else that's telling us about, okay, well, how much coagulant to add really depends on, well, how effective was it? And we might do some sort of a jar test. And actually, this is quite common practice in water treatment plants to just continuously have jar tests, or maybe once a day or a couple times a day, just to see, well, has the chemistry of the water changed much? How much coagulant do we need? What's the optimum dose? Because sometimes if we have too much of it, it's not going to work as well. If we have too little of it, it's not going to work so well. So in some combination, we need to just say, all right, here's the right amount. We don't need to do all of the calculations about what exactly is in the water if we just take a jar of the water and try it. Right? So it's quite empirical, quite simple, but also quite useful. So when we're thinking about, did we destabilize it properly? The ionic strength goes into that. Now we understand kind of how and why that works. We might add some other stuff, some polymers that could bridge over and grab the particles and stick them together. Whatever we do, now we have to give them time to mix. And so this is the flocculation. So at this point, we are primarily interested to know how many particles are there and what speed are they sticking together. That's going to let us design a system that allows them to grow big enough that we can sediment them. So it's all about getting particles large enough to let them settle out. And what we're going to do is a mass balance on the number of particles to say we have a lot and we want them to stick and make fewer larger particles. So in this case, we're going to reduce the number of particles by making them larger. Okay? It's kind of like playing one of those games as a kid where you're playing tag, but you like grab a hold of somebody, and then two of you are running around holding each other, and then you tag somebody else. You're making fewer clusters of people, but larger ones, right? Okay, so the question is, we're going to reduce this n over time, where n is the number concentration of particles, but how do we know the rate at which they're going to stick together? And so we're going to find a rate constant, but that rate constant depends on a few things. So today, we're going to derive that and then do some practice making use of that. So the first thing is the mixing conditions, right? I've already mixed my bottle a little bit. You can imagine if I'm mixing it slowly, I'm not putting a lot of energy in, I've got more gentle mixing than if I'm really turbocharging the mixer, right? And we actually want gentle mixing because we don't want to break the particles back apart. We want the small particles to be able to meet each other, but once they've formed larger particles, we don't want to be shearing them apart. So mixing intensity, we can describe as a gradient where we might have, let me do it this way. We might have some velocity of water flowing next to some surface. Maybe this is the paddle wheel that's doing the mixing. Maybe this is the edge of the reactor. And due to the forces of drag, we can say that, well, the speed of water is going to slow down as it approaches the wall. So at some point, this is going to taper off. But close to the wall, we're going to have a slow velocity term, where we have velocity this way. And in the y direction, we'll just call it y. This is distance from a surface. So we can then draw some gradient and say the slope here is dv dy. So that's the change in velocity per change in distance away from the surface. Okay? That's going to give us units. If we take this in, let's say, meters and seconds, that would be maybe a velocity term in meters and seconds and distance in meters. That yields 1 over seconds for our time, right? Per second time. So this is what we call G, or mixing intensity. We don't have to worry too much about the derivation here. I just want you to know this is where it's coming from. And conceptually, you can think about how fast the water is moving across next to the surface of my bottle. And there's a small gradient when it's doing this. There's a little bit of a difference. You know, it's not a very sharp gradient, but it's a bigger gradient when I speed it up, right? That's the thing. And you've probably felt this swimming in a pool or something. You wave your arm through. You can create a larger or smaller gradient, and it takes a lot more power to make a larger gradient, right? The difference between the speed at which your arm is passing through versus the speed of the water, which in that case is 0. So the equation for it has to do with power, the power that we're adding with a mixer. That's so the equation is the square root of P, the power, divided by the viscosity of water times the volume of the basin. Now, if you think about this, if you've ever stirred a jar of peanut butter, it's one of those like fancy kinds that's, you know, kind of the oil separates a bit. It's difficult to mix that, right? Especially without splashing yourself. But if you try to mix honey, something viscous, it takes a lot more power to mix it, right? Mixing dough if you're making bread, I don't know. Maybe I'm just hungry. The viscosity matters, right? And so it's going to influence the power. If you have higher viscosity, you need higher power to get the same mixing. Likewise, the volume matters, right? If you're trying to mix one small jar of peanut butter, that's not so hard, but if it was a giant tub of it, you're going to have to add a lot more power to get the same mixing effect throughout the whole system. So kind of obvious here, but the power, the volume, and the viscosity are the things that matter. And ultimately, because we're connecting it to this velocity gradient thing, whatever the units here are should give us per seconds. And I'm telling you that it does, right? So we have power in watts, dynamic viscosity in kilograms per meter second. that means we have to have volume in meters, cubic meters as well, right? So if we had a volume in liters, we need to convert that because we have to have matching units here for the watts and the viscosity. Okay, so that's the first parameter that goes into understanding how quickly particles meet and how quickly they form into larger particles. So we're still finding, we're kind of laying the groundworks so that we can find K for the particles meeting. So we got mixing conditions. That's one of them. That's coming into the K. And I want to take a moment to really remind us, what are we doing with that K? Like, what does that look like mathematically? What are we going to use for that K? So for particles colliding and making larger particles, what this will look like, if we just take some piece of the water, some little parcel here, and we have lots of little particles floating around, we want them to meet. Let's see, I have 1, 2, 3, 4, 5, 6, 7. What we want is for them to cluster up into one larger particle. So in this case, we have some initial n as 7 particles per little circle volume, right? So 7 particles per volume. And then after some mixing, after some flocculation, now we have 1 particle. It's just one larger one, right? So what we're saying is, like, we're decreasing the number of particles, thereby increasing the size. And the way we can describe this is to say we have 7 initial particles per final one. So how much larger is the final particle in volume? Yeah, just 7 times larger, right? So that's going to be quite convenient, and we'll see as an example today, we'll use the volume to get at the diameter because our velocity equation has to do with diameter. So we'll have to do a little bit of a geometry conversion there, but it'll make sense, it'll work fine. But it's really convenient if we just assume the particles aren't really changing size, they're just sticking together. We can still assume they're spherical. It's close enough. So if we create these larger particles, we're not losing volume, we're just gaining size, right? So we have a balance here on, we're not creating or destroying any particles, but we're reducing the number of them. So it's kind of like we're destroying them, but not really. So the way we can write this mathematically, to say the same thing that I just wrote, it's really convenient when we go and solve a mass balance to say, what does this mean mathematically? So this means n naught over n equals 7. There are 7 of the initial ones and each of the final ones. So given some volume, normalized by volume, because there's a volume term in both n naught and n, we have 7 of the initials in every final one. Now, a lot of times in our class, we will talk about n over n naught. How many are remaining? Well, that would be 1 remaining compared to 7, what we started with. It's not going to be as convenient to work that way because that's not as intuitive to say it out loud that way. So say it out loud, say 7 initial ones per 1 final. Just saying that, like when you're on the exam or doing a homework, that will make sense with how the questions are phrased and how we're designing the process. Now, we could also have a situation where we had, let's say, 6 particles, and now we have, let me say, do that again. We end up with 2 particles, each with 3 of them. In this case, we would have n naught over n equal to 3, or you could write it 6 over 2, right? For this particular case. So you can kind of see it doesn't really matter exactly the way we are, like the volume we're using. This could be 10,000 particles starting with, and 1,000 left, and then that's a factor of 10 or whatever, you can see how this ends up working out, right? And then we can connect with different mass balances to this n naught over n. So to get that mass balance, we need this k, right? So this will have to do with those collisions, and we're going to do mass balance so that we can figure out how many are there, so we can figure out their size, so we can figure out if they sediment. And to do that, we need this k, which we already started on, saying, okay, the mixing intensity is important. Well, there are a couple other things important, and I have another set of slides for that. Okay. Already covered this one. Okay, so what else is important? Well, this k will be a combination of that mixing intensity, and then we have this collision efficiency, alpha, I guess that's a lowercase alpha. The collision efficiency is basically the destabilization. When we talked about coagulation to allow the particles to stick together, this is how well did that work? How likely are they going to form a new particle when two particles meet? If they're completely stable, bless you, then they are doing the stiff arm thing and never touching each other, right? If they're stable, that means they're going to float around there and not settle. So completely stabilized particles would have a collision efficiency of 0, which doesn't quite make sense. So if we have 0, then they're not flocculating at all. So we're going to say that the collision efficiency should be between 0 and 1. Not equal to 0, because then they're not sticking. And then they could be 1, meaning every time two particles meet, they stick together and stay together. Okay, so this is a term. It's just a ratio. What percentage of the time we're going to use it as a fraction, right? Okay, so then we have a factor 4 there, and then omega. Omega is going to be the volume of your water that is occupied by particles. It's kind of a weird term. It's actually a volume ratio. It's going to be the portion of water that is, portion of your volume of water that is particles. So it's going to be, we call that the Flock volume. It's volume divided by volume, so it's technically unitless, assuming we do our number conversions correctly. So we have a collision efficiency, a factor of 4, the Flock volume, and the mixing intensity. We're also dividing by pi. So all of that put together will give us a unit for k in per seconds, because g is in per seconds and everything else is unitless. 4 and pi are unitless. This collision efficiency is unitless. It's a ratio. And I just said this guy is also unitless because it's a volume per volume. And the Flock volume situation can be understood this way. If 10% of my water is particles by volume, and I'm mixing it around, there's going to be a high chance they're hitting each other and mixing, finding each other, right? They'll meet each other quite frequently. If only like 1/100000th of the volume of water here is particles, there's like 2 particles, really tiny ones floating around, and they'll never meet, just about, right? It would take a very long time before they meet. So that rate constant would be very, very small. It would be very, very slow. Okay, so the Flock volume, this is actually, it looks a little complicated. You will have all these on your formula sheet, but it's actually kind of simple. It's the volume of one particle times the number of particles per liter of the initial ones. So we're always going to use the initial particles in this case. So this is going to be pi times the diameter cubed divided by 6. So that's the volume of a sphere, right? Volume of the sphere using the particle diameter, initial particle diameter. And then n naught is the number of particles per volume, right? And we're going to use the initial one, the initial particles for both the volume and this, because that's usually what we have the information on. So given that, what this is exactly calculating is the total volume of particles per total volume of solution. That we're, it's not like the total volume, but if we are measuring the particles per liter, then we're measuring that number of particles, the volume of that number of particles in that 1 liter. So this means that we need the volume of both, probably in meters or in some other similar units. So we have to make sure that this becomes unitless. So let's say cubic meters per cubic meter or something like that. Meters will probably be the most convenient, but I'll leave that to you. A lot of times you'll receive information like you'll have 10,000 particles per liter, and you will have the diameter of a particle in like millimeters, right? So you need to convert the liters to something that matches the millimeters, and probably you're not going to work with millimeters. You'd probably just convert that to meters and do cubic meters, right? So, yeah. So whatever you do, you have to make sure the units match. Okay, any questions there? So we've got an equation for K, which has 2 variables that we also need equations for. So it's a little complicated, but you'll have all these formulas. You just kind of need to know what they're talking about, right? So to get K, it's this collision efficiency, which will probably be given, I guess you could solve for it maybe, times 4, all that divided by pi, and then you have 2 variables where you have other equations, right? So you have the flock volume, and you have G. So G is the square root of the power divided by the dynamic viscosity of the water times the volume of the basin. And that's the square root of the whole thing, sorry. And the flock volume, as written below, that's pi dp cubed times n naught, all that over 6. So with those pieces of information, it's all stuff we could solve for. Just have to know what term is describing what. Then we can know the kinetics of how quickly the particles are meeting. Therefore, how long does it take for them to grow to large enough to sediment out of solution? So this can kind of pull all these pieces together with sedimentation and how to design it. Okay, so let's put it to practice. It's an example following from the last one we did. This is 6.2. It says to improve their settling, the 0.01 millimeter silt particles in that previous example are completely destabilized. That's a key word there. So complete destabilization, that's meaning that collision efficiency is going to be perfect. Right, so right there, I'm going to say collision efficiency should be 1. By adding alum, which is aluminum sulfate, and is passed through one of 2 side-by-side well-mixed flocculation chambers. The chambers are cubic, with each dimension being 3.5 meters. They are mixed with paddle mixers that input 2.5 kilowatts of power into the water in each chamber. The water entering the flocculation chamber contains 10 to the 5th particles per milliliter. And the question is, what is the average diameter of particles, or aggregates rather, leaving the chamber? So the aggregate would be the particle after it's stuck together with other particles. Okay, and from the prior problem, we know that the total flow rate is 3 mgd, and we have that conversion, and we have the dynamic viscosity of water. So this is a pretty involved problem. I've got more space for us to work on it, and then a couple other thoughts. So I'm going to give you a little bit of time. You're welcome to work together. After a few minutes, I'll start kind of writing up a few of my own notes. But take a few minutes to see if you can take a strategic approach here, right, to solve this problem. You're welcome to ask me any questions. You're welcome to work together. But I want to give you some time to work on this in class now. Right, so you see I've kind of written up a few things like what do we need to solve for to begin with. Once we get those, and I'm going to just put this into Excel here in a moment. Maybe I have an old copy of it, I'll check. But once we get there, we really need to then set up a mass balance. So hopefully you kind of recognize some of these things you need to solve for. Yeah. We had a 3.5 cubic, did I do that wrong? So, oops. So what I tried to do is 3.5 times 3.5 times 3.5. And I just didn't hit it in the calculator right, so thank you. I think what I did was 3.5 times 3.5, and then I hit enter again, and I guess that just didn't do the right thing. Good catch. So it should be 42.9 or 875. Okay, so my mistakes aside, you ought to be thinking to yourself, okay, I need to solve for these variables because we just learned that and we're going to need those. But bigger picture, you should also be thinking, well, how are we going to find that new concentration? And one thing I'd like for you to practice doing is when you encounter a problem, draw it out. Draw out some sort of schematic. Where are things going in? Where are things going out? And I did that up here at the top. We had two side-by-side reactors that are treating this flow. So we could think to ourselves, okay, I have two reactors to deal with, but the simpler way to go about it would be to say, well, these are identical. Whatever happens in one is the same thing that's happening in the other. So let me just split the flow in half. And it does say, I think, equal flows. So the flow will now be 1.5 mgd on each. And consider one reactor. Okay, we know the dimensions of it. We know that one reactor. Let's solve a mass balance on one of the reactors in order to figure out some ratio between N and N naught. If you recall when we did some mass balances, and as you've practiced some with the homeworks, we often solve for something like N or C. And usually that's a function of N naught or C naught or something. So there's no reason we can't find some ratio of those two with many of our mass balances. So what we're going to want to try to find is a mass balance on N to get something like N naught over N. So be thinking about that as I pull up the calculations and fill in these numbers here. And see for yourself, like, can you get there and can you start solving that? Because once we have something like that, then we can make a comparison to the size of the particles. That's kind of the trajectory of this. All right, so I've gotten pretty far now for you here, and I'll share what it looks like in Excel. So essentially, I put things into here, went ahead and put several of our parameters, did a few conversions, the volume of the basin, the number of the particles, converted the number of the particles to particles per cubic meter so that I could get that flock volume unitless. I sort of did that on the previous slide. It showed that I was working towards that. You have to convert from milliliters to cubic meters. That's a pretty large number. But to counter that, that times 10 to the minus fifth value for the diameter was being cubed. So that counterbalances with kind of a small number. So at any rate, your number of particles is pretty high, but the flock volume, omega, is a small portion of the volume of your solution is particles. So it makes sense that maybe 1/10,000th of your bottle of water has is volume that is particles, right? If you have a complete slurry, then you still have a lot of volume of water there, but there's a fair amount of particles. So maybe that gets closer to 1. If your volume is particle, then that should become 1, and you should never have higher than 1. So you can kind of double check your flock volume. It should be a pretty small number. Positive, but small. The G value came out to be 225. I put these up there, and then if we calculate the K from that, it's 0.015 per second. So a lot of those, that's just calculations. I have them in Excel, so hopefully they're not wrong, like I was wrong at first with the volume. The built-in calculator always seems to give me trouble. I like Excel instead. Then we're moving on to solving the mass balance, right? And I kind of wrote that here to say, all right, well, what is this mass balance? We weren't given any information about the system being changed or faster, slower, anything weird. So we can kind of assume it's just going to be a steady state. That's a fair assumption. I went ahead and said, let's assume steady state so that we have no net accumulation. The thing is continuously flowing. It's kind of just going about its business. So then our mass balance would be 0 is what's coming in minus what's going out plus the reaction term. Now here's where you have to apply what you know, right? Because we first of all think to ourselves, okay, it's continuous flow and it's being mixed. So it should be a CSTR, right? If we look at the system, we ought to recognize that's a CSTR, and that's why we're building the mass balance this way. Now the reaction term we also have to think about because we're maybe not sure exactly what reaction order this is working in. Now, a couple things you could think about. One is whether or not this type of reaction will depend on the number of particles there. Well, just by describing the system, I already told you if there's not many particles there to meet each other, it's not really going to happen because they have to meet each other. So physically, it should depend on how many particles are there. Physically, that means it should be probably a first order. But more technically, we have a rate constant with some units, right? Our K is per seconds. And we had derived that from the expression that G is in per seconds, and that's what it depends on. So the fact that we are in per second units for our rate constant here, that tells us we're in a first order reaction, right? Based on that derivation. So that means when we set up our term here, we're going to put a 1 raised to n to the power of 1, or just leave it as n, same thing. So it's a first order decay reaction then with respect to the number of particles, because we're decreasing the number. So then we can solve this just like we have with some other mass balances, except this time I'm interested in isolating n naught and then dividing that by n if possible. So I went ahead and said, let me just get the n terms together by themselves on the left. So add both of those over. So I get Qn plus Vkn equals Qn naught. Figured I'd go ahead and divide everything by Q at that point. That gives us, drops the Q term, so it becomes N plus V over Q, which is theta, Kn equals N naught. After that, you can just divide everything by N. and you have an expression that we can use to make the comparison that we need. So n naught over n is equal to 1 plus theta k. We can solve theta. Remember, we're routing half of the water through, so that's 3.5 divided by 2 is 1.5, 3 divided by 2. It's 1.5 mgd. So I went ahead and solved that here. V over Q, volume of that one chamber, divided by half the flow in the entire system. That should be 652.6 seconds. Okay, from here, now we can solve for n naught over n. And remember, what I said is this is saying we have this number of particles, of the original particles, in each one of our aggregates. Right, so this number will tell us how many times the volume has multiplied. And from there, we can solve finally for the answer to our question is, well, what's the average diameter now? So let me come back to my Excel sheet, and we'll see that n naught over n, when we plug that in, should be 10.82. So we could write this, and it might help to write this as if it had units. This would be initial over final particles. Right? Okay, from there, give it a moment to see if you can solve the final question about the diameter. How would you do that? Okay, so it should look something like this, where we say the volume of a sphere is pi over 6 times the diameter cubed. And we can say then that in addition to that, So that'll give us a term we can use to find the diameter. In addition to that, we can say that the volume of each aggregate is 10.82 times the volume of each individual particle, of the starting particles, right? That's the relationship. We know we're not losing any size of these particles. So that means we can set this up to say the volume of the aggregate in terms of the diameter of the aggregate is equal to that 10.82 times the volume of the particle. So with this, we can set up and get the diameter of the aggregate, cancel a few things, set it up as the cubic root of 10.82 times that diameter term cubed, and that should give us a final answer of 2.21 times 10 to the minus fifth meters. Now, if we notice that we had 1 times 10 to the minus fifth meters for the original, right? So the diameter changed by a factor of about 2.2. So 2.2 times larger, that means they will sediment faster, and perhaps that's good enough for the problem. Does that make sense? Any questions or issues? Okay, so quite an involved problem here. I have one other thing I want to just quickly mention. If we have sequenced reactors, it's a little different than parallel reactors. So we just did one with parallel reactors. It is possible for us to sequence reactors. I think I'll go a little more in depth on this at a later time, but we do see this with coagulation and flocculation chambers in particular quite often, where we would have some initial, some intermediate, and some final. And if these are exactly the same types of reactors, the math can actually become quite simple, combining these together. I'll come back and talk about this at some other point, and make sure you don't need that for, maybe I'll add that to our homework review. But, all right, have a good weekend. See you on Tuesday.